Welcome to MOVITRAC LTP-B Basic and Intermediate Training. This is Session 10. As I said at the end of our last session, we're now transitioning to more advanced concepts, and we're going to begin them today by learning about a tool that's built into the VFD. It's useful for both diagnostics, troubleshooting, and general purpose work. It's called the scope. So we're going to be looking at the scope. We're going to see some of the things you can do with it, and I'm going to demonstrate it in several different ways. So let's begin talking about what the scope is and how it works. So what's the scope for? Why is it built into the VFD, and what might you use it for? The scope works a lot like a multi-channel bench oscilloscope. If you've ever used an oscilloscope, then this should be very familiar ground, but if you haven't, it's not a big deal. I'll be explaining how the scope works, and I'll be demonstrating it very thoroughly, so you'll be able to use the scope like a pro by the time you're done with this class. These are the things you typically do with the scope tool. You can use it to confirm that everything works, so in other words, you've set up your VFD with your application and you want to be sure everything is working as expected. The scope gives you a visual confirmation and possibly measurement confirmation as well that everything is behaving as expected. You can use the scope to optimize the performance of your VFD, for example, adjusting things like ramp timings and making sure that the load is accelerating and decelerating as expected. You can also use this scope in diagnostic and troubleshooting mode. You can use it to identify abnormal behavior, finding out why something is happening. You can also use it for troubleshooting difficult faults. Let's say you have a fault that only happens once a week. Obviously, you can't camp out and watch the VFD for a week, but the scope can do exactly that. You can set it up to watch for the particular problem and then collect data surrounding that event. Then at your leisure, you can come back, analyze it, and figure out why that fault happens. So that's just a few general ideas as to what the scope is good for. We'll be digging into it in much greater detail as we go along. All right, let's talk about the scope. I want to give you a general overview of it and how it works, and then we'll get into some of the details. First of all, a few scope facts. The scope is actually built into the VFD. It's within the hardware of the MOVITRAC LTP-B. Now, yes, you use the LT shell program to visually display the information it collects, but the scope is within the VFD. Now, you may wonder, why am I making such a point about that? Well, there's a very good reason. The scope does not require a PC to be connected to the VFD to collect data. The PC, in fact, is used only for two things. It's used for setting up the scope and getting it configured, and then later for displaying the data after you've collected it. What this means is you can configure the scope with your PC and LT shell, then unplug it from the VFD, walk away, come back later to collect the data and look at it. That means you don't have to leave a laptop plugged into the VFD, possibly for days if you're tracking down a problem. So having the scope built into the VFD is actually extremely beneficial. Now, the scope built into the VFD is actually quite powerful. It has 4 channels, so it can monitor 4 VFD parameters at one time. Now, you don't have to monitor 4 parameters at once, but you can definitely monitor 4 parameters if you need to do this. In general, it's a great idea when you're trying to solve problems to collect as much data as possible. So I urge you to take advantage of the fact that the scope can monitor 4 things at a time. These are the parameters you can monitor. There are 75 of them, and that's a lot. Now, many of these you probably would hardly ever have a need to monitor. So I'm going to point out some of the ones that you will use fairly frequently. They are these: the DC bus voltage, it lets you monitor the DC link, the heatsink and internal temperatures, the motor current, power, speed, either in Hertz or RPM, and torque. These are the ones you'll probably use most of the time, but it's conceivable you could use any of these. So I'll be showing you how to pick the parameters you want to monitor and how to interpret the data once you have acquired it. The scope has 2 modes, and they serve completely different purposes. I'll be demonstrating both of them. Continuous trace mode is kind of like a classic laboratory bench oscilloscope where the data is just displayed continuously in real time. You press the start button and the scope display on the PC immediately starts showing the traces, and it just keeps going and going and going as long as you want. This is really handy when you're setting things up just to confirm that the VFD is working as you expect. So this is kind of the simple mode to use the scope, real-time continuous trace mode. The second mode is called triggered capture mode. Laboratory oscilloscopes can do this too. What happens, the scope doesn't actually collect any data until an event occurs. Now what that is up to you. It could be a specific fault, it could be a digital input changing, or it could be a parameter value changing to a specific level. Doesn't really matter, you set up the trigger, whatever happens to work for you, and what the scope will do is it will collect data around that trigger event, store it in its memory, and then when you download it in LT Shell, you can analyze what happens surrounding the trigger event. As you can guess, triggered capture mode is especially useful when you're troubleshooting faults. Let's begin by looking at continuous run mode, which is the simpler of the two modes, and then later on we'll take a look at triggered capture. As I've said, continuous run mode is good for monitoring the drive and confirming desired behavior. This is the screen as it appears when you are in continuous run mode. Now the way you set it up, you select the mode, you change capture mode to continuous run. Then you pick your channels. I have only two assigned here, motor speed and RPM and motor current and amperes. The other two are turned off. Notice each channel has a different color. It matches the color of the trace on the screen. Once you have that set up, you press the Start/Stop button and the scope will immediately start displaying data. You can watch the data as it appears, and if you want to freeze it, just press the Start/Stop button again. It will halt and the data will remain frozen on the screen for you to analyze. You can position the individual traces vertically. Each trace has a colored arrow next to it. You just click the mouse on it and drag it up or down to move the traces. You can also zoom the trace by moving the two vertical bars next to the small window at the bottom of the screen. This allows you to zoom in and out of a particular section of the trace. Very handy when you're taking measurements. You have two measurement cursors which you can grab and slide with the mouse. One will be on the right side of the screen, one on the left. Position them on the traces and what will happen is the value at the position of the cursor will appear in the channel windows. Because there are two cursors, you can also use them to measure the time difference between 2 points on the trace. Very handy if you're measuring ramp values. Let's look at these controls in a little more detail. If you click the blue button next to a channel, you can open and close its controls. Notice motor speeds controls are open, whereas motor current below is closed. When you click this, additional controls will be revealed. The scale buttons allow you to increase or decrease the vertical scaling of the trace. If you click the Enable Auto Scaling checkbox, the trace will automatically scale to fill as much of the window as feasible. And the value at the cursor will be shown in the channel window. Whichever cursor you're currently sliding is the one whose values will appear in the windows. Right now, I have grabbed this cursor on the right, and so what that is saying is the place where that crosses the red trace, which is the motor speed, is 835 RPM at that point, and where it's crossing the green trace, which is the motor current, is 0.43 amperes. Now, if I were to grab the other cursor, the values would change to reflect what it is doing as it crosses the trace. Notice the cursors both have time values. These are the time values of their current position. But also notice the first cursor has a little triangle. That's a Greek letter delta. And there is a number there. That is the time difference between the two cursors. So if you wish to measure, for example, a ramp value, you can position one cursor at the beginning, one at the end, and then look at the delta value, and that will tell you how long the ramp took. So I think it's time for a demonstration. I'm going to go into the scope in continuous capture mode, and I'm going to show you how to do a few of the things I've just talked about. So let's duck into LT Shell. We need to get our VFD configured to work with the scope, and then we'll go ahead and collect some data and analyze it. Okay, well, we're in LT Shell and we're already scanned in. We're right where we were at the end of our last session, so we definitely need to change a few things to play with the scope effectively. So let's turn on real-time edit mode and make a few changes. I'm going to leave us in terminal control mode, so parameter 1-12 can be left set to 0. But I want to get rid of my custom define mode that I did last time. I'm going to change to variant 6. This one is good because it lets us pick preset speed 1 or the potentiometer, and it also lets us monitor a fault sensor. So we're going to use that for all our activities. We'll pick 6. I'm also going to change our acceleration and deceleration ramp times. I'm going to change the acceleration time from 2 seconds to 8 seconds. And I'm going to change my deceleration time to 2 seconds. All right, now I'm going to go to parameter group 2, and I'm going to change preset number 1 to 1500 RPM. Now I'm doing this very intentionally because when you set the VFD to 1500 RPM, that means the ramp times are the actual times that the acceleration and deceleration events will take. So that means back here, if I pick preset speed number 1, it's going to take 8 seconds to accelerate up to 1500 RPM and 2 seconds to decelerate back down to 0. All right, and we're going to use the scope to confirm that that really works. I need to change one other thing, so I'll go back to group 2 here, and I need to go and get rid of that bidirectional potentiometer mode. So I'm going to change parameter 2-30 to 0 to 10 volts. I'll change 2-31 back to 100%. and 2-32 back to 0%. And that's all we have to do. We now have everything configured properly so we can play with our VFD and watch its behavior on the scope. Let's turn off real-time edit mode, and let's bring up the scope tool. So here we go. Now we need to assign some channel values, so we're going to use just 2 channels for this activity. I'm going to set channel 1 to my motor speed and RPM. So I find motor speed and RPM, and I pick that. And for channel 2, I'm going to pick motor current in amperes. And that's all we're going to look at for this particular activity. Now you can see we're already set up in continuous run mode, so we're all set to go. If I click the Start button, the scope will start collecting data. Now you can see it's all clustered down there at the bottom of the screen, which isn't too nice, but we'll change that eventually. And it's just going to keep collecting data. It'll do this all day if I let it. What I'm going to do now is go to my VFD. I'm going to turn it on by enabling digital input 1, and I'm going to pick the preset speed. So what's going to happen when I enable it, it's going to accelerate from 0 to 1500 RPM. I'll let it run for a few seconds, then I'll bring it down again. We'll stop the trace and we'll take some measurements and see if those ramps are what they should be. All right, so that's what we're going to do. Digital input 5, by the way, because it is the fault sensor, has to be turned on so it doesn't trip. I'll be sure to do that. We'll go ahead now and collect some data. So there we have our data. We have our 2 traces. First of all, let's get the traces a little better arranged on the screen so we can work with them. So what I'm going to do first is adjust my horizontal zoom by sliding these vertical lines here to limit what's on the display. The bottom window shows the entire capture buffer. The top part of the screen shows whatever's between the lines. So this effectively lets me zoom in on the trace. I'm also going to separate my traces. I'm going to grab the little green arrow here on the right side, click it and drag it. That's the motor current. I'm going to move it up out of the way. I'm going to move the RPM value up a little bit too. Let me show you the channel controls here. I'll open motor current by clicking it, and notice I can scale my values up or down like this. I can also auto scale them if I want, or turn that off. So I'm going to adjust my motor current a little bit here. But again, I'm going to adjust it so it's not overlapping the motor speed. So there we go. We have our 2 traces here. Let's take a few readings here. I'm going to grab one of my cursors that's over on the left side. I'll just grab it and slide it, and I'll pick a value right here. And you notice the motor speed where it crosses the red trace is 725 RPM. And the motor current where it crosses the green trace is 0.41 amperes. So as I move this, it changes to show what the plot's value is at that spot. If I grab the other cursor, the value now displays it where it's crossing the trace. So let's do something here. Let's take a measurement on that up ramp and let's see if it really took 8 seconds. What I'm going to do is zoom in a little more so we can get an even more accurate view of this. So I'm going to move my left cursor to the point where the RPM value just starts to change. So I'll move it until that value moves off of 0. All right, so there. Right about there is where it starts to change. I'll move the right cursor to where it levels off at 1500 RPM. That's about here. All right. And I look at my delta value right here and 8.8 seconds. So maybe actually the cursor really should have been more like here, I guess. 7.9 seconds. There we go. That actually is pretty close to 8. So you can see we're able to confirm the ramp value. Let's check our other ramp value here. I'm going to move my zoom here so we can concentrate on the down ramp. I'll move my left cursor to where the line just starts to head down. It jumps around a bit, unfortunately, so it's kind of hard to know where it starts. We'll just put it there. And we'll put this one about here, and you can see, there we go, 2.26 seconds, pretty close. So that is using the scope to take measurements such as time values on ramps or actual values off the channels. Pretty nice, pretty simple. All right, well, we've taken a good look at continuous run mode. You can see it's relatively simple, but definitely a handy tool. Now we're going to pivot and take a look at triggered capture mode, which is definitely a little more complicated. If you've never worked with a laboratory oscilloscope before, you may find this mode a little bit baffling at first, but just hang in there. I'm going to try to give you a very thorough explanation of how it works, and you will discover this mode can really be your friend when you're trying to crack a difficult problem. Okay, so this is triggered capture mode. The screen is slightly different. Let's go over the controls. In triggered capture mode, the scope waits for the trigger. Now that's a very important term. It's a specific event that tells the scope to start collecting data. Trigger can be many things. It can be a fault, it can be a parameter value change, or a digital input edge. Any one of these things can tell the scope to start collecting data and storing it in its memory. You can visualize what's happening sort of like this. The trigger is like pressing the shutter button on a camera. When the trigger happens, the scope takes a snapshot of all the channels you've configured, preserving data from periods before, during, and after the trigger. And it stores all this in its memory, and then later when you go into LT Shell and download it, you get the trace on the screen, and then you can use it to figure out what's going on. Now, some very important concepts here and some terminology. The pre-trigger data is the percentage of data in the scope's memory from the time period before the trigger event. The post-trigger data is the percentage of data in the scope's memory from the period after the trigger event. And you set the pre- and post-trigger values by adjusting the pre-trigger percentage. So you set the pre-trigger to some value, say 30%. The post-trigger is going to be 100% minus that value. So if the pre-trigger is 30%, the post-trigger will be 70%. You set it with a simple adjustment, and that sets both these values. Now let me explain how triggered capture works. This is actually kind of interesting when you dig into it. What we're going to do is sort of talk about what the scope is doing behind the scenes. Think of the scope sort of like a camera. It contains some capture hardware that electrically monitors the 4 parameters that you have selected from within the VFD. Let's say, for example, that we're going to monitor the motor's speed, current, torque, and the DC bus voltage. You can monitor a maximum of 4 parameters at a time. You pick these, and the capture hardware is going to start monitoring those 4 things. The capture hardware is going to dump the number values of those parameters into its memory. The scope memory has 4 independent channels to hold the information that it captures when it's monitoring those parameters. So what the scope is going to do is going to take a snapshot of each monitored parameter and store that value in its memory. So it's kind of like this. It starts taking snapshots of the 4 channels, it turns them into numbers representing the values, and it dumps them into its memory. So there you go, that's a capture cycle. Now here's another important term, sample rate. This is how often it takes a picture. So the sample rate is adjustable. The capture hardware can take samples very close together, or it can take them at very wide intervals. The faster the sample rate, the better the quality of the trace, but because the scope's memory is not very big, the faster it fills its memory. And once the memory's full, you're done. Generally, you have to adjust the sample rate to strike a compromise between the quality of the trace and the amount of memory you have. In other words, how long the trace can be. Let's dig into this a little more deeply. Now, when you set the scope up, when it's idle, it's actually endlessly filling its channel memory. It uses a technique called circular buffering, which means it fills the memory and then it wraps around back to the beginning, overwriting the oldest data first, so it just keeps going around in a circle. Let me demonstrate that. Our scope is collecting data, it's filling memory, it's coming to the end, and notice now it goes back to the beginning and starts overwriting the older data first, goes around again, overwriting the older data first. It's just a big ring. And it's just going round and round and round. It does this forever. And what it's doing is it's waiting for the trigger to tell it when something important has happened. So while endlessly filling its memory, the scope is watching for the trigger. And you define what the trigger is. When that happens, the scope will change its behavior. So when the trigger occurs, what the scope is going to do, it continues collecting snapshots until it reaches a point in memory where the pre-trigger percentage is located, and at that point it stops. Now what does that mean? Let me demonstrate. Let's say we set our pre-trigger percentage to 20%, which means our post-trigger percentage is automatically 80%. That means that the scope's memory, when we're all done, will contain 20% data before the trigger and 80% after. The scope is collecting data. It's just going round and round and round, waiting for the trigger. And then all of a sudden, boom, the trigger happened right there where the red arrow is. Now at this point, here's what the scope does. It marks 20% of its memory before the trigger so it will not get overwritten. So these two numbers here are 20% of the memory. They get marked so they will not get overwritten. Then what the scope does, it just continues collecting data, the blue data, until it comes to the green data, and then it stops. At this point, it has 20% pre-trigger data, the data at the trigger, and 80% post-trigger data. The memory's full, so it's got to stop. When LT Shell downloads the scope memory, what it does, it organizes it in the correct sequence and identifies where the trigger is located. So it plays it back on the screen sort of like this. And this is the complete trace. Now these numbers are then turned back into the trace, which is displayed on the screen, and you can take measurements from it, and of course you can visually inspect it. The trigger is indicated by the little white arrow. That indicates where in time the trigger event occurred. So with this particular trace, about 90% of the data is pre-trigger because it's to the left of the arrow, and 10% is post-trigger, which is to the right of the arrow. As you can guess, setting up triggered capture requires a little more work than continuous run mode. It's not that hard, but you definitely have to set a few more things. Let's talk about them. All right, you go down here to the corner, and first of all, you have to change it from continuous run to trigger on event. So you select the mode. Then you pick the trigger type, and these are the possible trigger types. A trip, which is typically a fault, a level on the parameter monitored by channel 1, or a change in one of the 8 digital inputs. If you pick trip, then you can pick which trip type. You could say any trip, or you can pick from a list of trips, and you've seen some of these before. Now, if you pick one of the digital inputs, then you have to pick an edge selection, whether the signal is rising from a low to high or falling from a high to low. If you want to trigger on the level on channel 1, then you can set the value. For example, let's say you're monitoring RPM on channel 1 and you want the scope to trigger if the RPM goes over 1,000 RPM. You would set the trigger level to 1,000 RPM. The sample rate is set by this pull-down box, and right below it is the amount of time that the total trace can be. So you need to pick a sample time that gives you a long enough capture period to show you what you're interested in. And then finally, you set the pre-trigger percentage down here at the bottom. Right now it's set to 10%, but you can set it anywhere between 0 and 100%. Post-trigger, of course, is 100% minus that value. And then finally, sort of like cocking a gun, you click the Start button and the VFD Scope tool will start waiting for the trigger. And at this point, you could actually unplug your PC and walk away. The scope would be primed and ready. So setting the pre and post trigger percentage, as you can guess, is kind of important because it determines what you get. Here's a piece of advice. Set the pre and post trigger percentages to emphasize what you're interested in. So for example, if you set pre-trigger to 90%, this means 90% of the data comes before the trigger and 10% comes after. What you're doing here is emphasizing what leads up to the trigger event. When you're tracking faults, this is generally a good combination because you're interested in what led up to the fault, not what happened after. Maybe you want to see how the VFD handles shutting down, which is why you collect 10% after, but most of your data comes before. On the other hand, you could do the opposite. You could set 10% pre-trigger and 90% post-trigger. In that case, what you're seeing is what happens mostly after the trigger event. Maybe you've set your VFD to trigger on the speed rising to a certain level, and you want to see what happens after the speed has risen. In that case, this would work really well. Alternatively, you could just set it to 50%, and then you get a good look at what happens both before and after the trigger. It's up to you. It depends on your application. So I think I need to demonstrate this. I'm going to demonstrate 3 different ways you can do triggered capture. We're already set up an LT shell. We don't have to change our VFD at all, so we'll just go straight to the scope. We'll configure it. We'll do our 3 different captures and see what we can learn from them. Okay, well, we're going to play with triggered capture mode. We don't have to change anything in the VFD. The way it's set up is just fine to demonstrate this, but we definitely do have to change modes in our scope. We're still set to continuous run mode, so we're going to pop this down and change it to trigger on event. Now we're going to do 3 different triggered captures. I'm going to demonstrate 3 things to you, but what I'd like to begin with is triggering on a fault. So we're going to trigger on a trip. Now, the trigger event is already set to trip, so that is fine, but the trip type is set to any trip, and I want to be more specific than that. So I'm going to pull this down and pick external trip. We're going to use the eTrip sensor. Remember, that's digital input 5. I have a potentiometer on that, and it's turned all the way up right now. So all I have to do is turn it down, and that will fire off this particular event, and we'll get a capture. What I'm going to do is I'm going to start my VFD up. I'm going to put it in potentiometer control mode. I'm going to ramp the speed up and down a few times, and then I'm going to trigger a fault. Now we do need to set our sample rate, and right now it's set to 10 milliseconds, so it's taking a snapshot every 10 one-thousandths of a second. That gives us a total of 5 seconds of data in the memory. That's a fairly short trace. So what I'm going to do is change this from 10 milliseconds to 20, and that gives me a 10-second capture. So the quality is a little lower, but it's longer. I need to set my pre-trigger. Right now it's set to 90%, which means 90% of the data will come before the event and 10% after. I'm going to adjust it actually to 95%. When you're capturing fault information, you want almost all your data before the fault. You just want a little afterwards to kind of watch the aftermath of the fault. So that's fine. I'm also going to add one more channel here just for fun. I'm going to change my 3rd channel to the DC bus voltage so we can monitor the DC link. I don't expect to see anything interesting on it since we're not generating a genuine fault. But in real-life applications, it's very useful to monitor the motor's speed, current, and the DC link voltage. All right, we're all set to go. I'm going to click the Start button to prime the capture. And you see there it is. It's waiting for the trigger. So I'm going to go over to my VFD, start it up. I'll play with the speed a bit, and then I'll trigger a fault, and you should see it immediately appear on there as soon as I've triggered it. Here we go. All right, well, you can see the trigger arrived, and now LT Shell is downloading the data from the scope and the VFD into the PC. This is kind of a slow process because the communications link between the two is not terribly fast, so you just kind of have to wait this out. But once it's downloaded, we'll have our trace on the screen, and then we can take a look at it. All right, there we go. Let me take our DC link value and slide it up. And I'm going to adjust it so we can see it a little better. It's not very exciting because not much is happening. I'll turn auto scaling on there and you can see it right there. Now I'll turn this off. and I'm going to slide it down a bit and maybe adjust it. There we go. There's our DC link value. If I slide a cursor over it, you can see it's pretty steadily at 630 volts. Doesn't change much because we're really not doing much. Notice the motor current jumps around a little bit. Notice the speed ramps up and down. And then here we can see our trigger event, the white arrow. Notice that 95% of the data comes before the arrow. That's the activity leading up to the fault. The fault occurred at the arrow, and then that 5% afterwards just shows the VFD shutting down. So there we go. That's a typical fault capture where most of your data comes before the trigger, and that's just one classic example of how you can use the scope. All right, we're going to change our trigger event to something else. We're going to use one of the digital signals to trigger it. We're going to use digital input 3. In this particular mode, it switches between the potentiometers, the speed control source, and preset number 1. So I'm going to change this to digital input 3, and I'm setting it here to the rising edge. So I'm going to start in potentiometer mode. I'll ramp the speed up and down a few times, then I'll switch to the preset speed. That will trigger the scope, and what we're going to see is data before that and after that. I'm going to change my pre-trigger percentage to 50%, and that means that half my data will come before digital input 3 turned on, and half of it will come after. So we're going to see everything surrounding digital input 3 rising. Here we go. Let's click Start. And let's go switch on the VFD. Okay, and you can see we've been triggered. We're now downloading the data, and we should see my playing with the potentiometer on the left side of the screen, and then that steady ramp up to 1500 RPM on the right side. And there we go. Our trigger event is right here in the middle. So before this, you can see my playing with the potentiometer. And here you can see the VFD just ramping steadily up to 1500 RPM. And then I switched off here and it started to go down, but we ran out of time, and that's where the trace ends. So that is triggering on a digital input. Now the last trigger type I'm going to show you is triggering on a level. So what we're going to do is we're going to trigger on the level of channel 1, which is our motor speed. And I'm going to set the trigger level to 1000 RPM. And so what will happen is the scope will just sit waiting for the speed to rise to 1000 RPM, and at that point it will start collecting data. I'm going to set the pre-trigger to 50% again. We'll see what happened before we reached that speed, and we'll see what happened after we reached it. I'll leave the sample rate where it is. 10 seconds is fine. I'm going to start the scope. So it's waiting for a trigger, and here's what I'm going to do. I'm going to switch to potentiometer mode. I'm going to play with it, ramp it up and down a little bit, but I won't cross 1000 RPM right away. I'll do that a little later, and that should trigger the scope at that point. Here we go. Okay, you can see we triggered, and we're now downloading our data. And there we go. So you can see I was playing with the speed here, and then at this point I turned it all the way up and it started accelerating. Let's put the cursor right on the trigger and see if that really happened at 1000 RPM. And it happened at 988 RPM approximately, so yes indeed, it triggered where we expected. So that is triggering on a level. So these three examples pretty much illustrate how to use the scope in triggered capture mode. All right, well I hope you found that interesting and helpful, and I hope you're inspired to go out there and start playing with the scope. If you have a demo unit, I encourage you to go and try to repeat some of the things I've just done. Get some experience. The more you use the scope, the better you get with it. We're almost done with this session, but there are a few miscellaneous topics I want to cover about the scope before we sign off, so let's cover these. I've mentioned several times that you can set up the scope to collect data over a long period of time, and you don't have to leave your PC plugged into the VFD. I'm going to show you how you set that up right now. What you do, configure the scope, get everything set up, set the trigger, and then click the Start button. And then what you can do is close LT shell, unplug your cable, and walk away. Now later on, when the trigger event has occurred, the scope will hold the trace in memory until you come back to collect it. How do you know if there's a trace waiting for you? Well, connect up to your VFD with LT shell, scan in. If you go to parameter group 0 and look at parameters 0-29, you will notice there's a line there that says scope capture data available. And in this case, it says yes. That means there's a trace in memory waiting for you. If it says no, obviously there isn't. What you can do then is switch to the scope mode and click the button in the upper corner that has the green arrow pointing out of the VFD. What this will do is it will download the data from the scope's memory into LT shell and give you a visual portrayal. And at that point, you can start taking measurements, use the cursors, whatever you like to figure out what's going on. A little warning here. Do not turn off the power from your VFD. The scope trace will be lost. So if you were trying to collect a trace before you do anything else to the VFD, plug into it, download that trace, and then you can do whatever you need to on the VFD. But otherwise you could lose your hard work. So you have been warned. Something that's very helpful to do, and you may have to do this from time to time, especially if you're talking to a technical support engineer at SEW Eurodrive, the engineer may ask you to save a scope trace and send it by email so it can be analyzed by an expert. So can you do that? Absolutely. Here's how you do it. All you do after you acquire the trace is you go to the toolbar at the top of the screen and you click the little old-fashioned floppy disk icon, and that will allow you to save the trace. And if you want to open a trace to look at it yourself, or someone emails one to you, just use the little open folder icon to open the trace, and you can look at it right there in the scope. Incidentally, scope traces are given these really long but highly descriptive file names. Notice they tell what kind of VFD it is, they tell its voltage, its horsepower rating, its firmware version, and its address. And then they end by scopeplot.plt. Of course, you can change to a shorter file name if you like, but these long names are actually helpful because they encode a lot of information. That is something you might have to do. Now you know how to do it. And that is the end of session 10. I hope you found that interesting. I really like this scope. I find it a fun tool to use, and I hope you find it useful in solving your problems. In our next session, we're going to start learning about field bus communications with the MOVITRAC LTP-B. We'll learn about the different ways to get onto a field bus and how to set them up. So, see you next time.